completed my PhD and submitted my thesis under the guidance of Dr. Ashwata Prabhu. And today I am going to give you a demo on the topic of diffraction of light at the single slit. So what do you mean by diffraction? Diffraction is a phenomenon where the light is coming from a distance and there is an obstacle in between them which will make the light to bend towards the other direction with a different wavefronts, and that will form two types of fringes, like dark fringes as well as bright fringes on the screen. So this is called diffraction phenomena in our physics, and here we are going to take the diffraction of light at the single slit. So we are taking only the single slit by Wing's experiment. So let me draw a diagram for you. So this is a light ray coming from a distant source. This is the slit where the light will be bending towards the other direction with different wavefronts, and the images will be formed at the, or the fringes are formed at the screen. Okay, then here again some light ray is coming and then it is bending towards the other direction. So this is called diffraction phenomena. So pertaining to single slit experiment, consider a slit of distance A. Okay, then there is a screen which is comparable to the distance of these two, source and the screen. Then the width of the slit should be comparable to the wavelength of the light. So what is it? The light is coming from the source, which is a principal axis. We can give the name C, and here we can give the name O. Then the light rays coming from the edge of A are having the diffraction and they will meet at point P. Then there is one more light ray is coming from the B and they will be obstacled by the slit and they also get diffracted and they will meet at P. Later, one more principal axis we are drawing for the purpose of our reference, so which also will meet at P. So totally we have three kinds of rays, and then the parallel rays which are moving towards the screen with no diffraction, and one more parallel ray moving towards the screen. Okay, then we have to draw a perpendicular line towards the A to B. So I am drawing a perpendicular line. So here we get the one kind of a triangle, which is a right angle triangle. We can draw a perpendicular line for this, and we can consider this angle as theta, and this can be considered as theta. This can also be considered as theta because they are all corresponding angles, as well as which are having the parallel lines A to the screen and B to the screen. So this is all about the diagram, and the distance between the width slit and the screen should be D. So the next process is the formation of the equation. Consider the triangle. I am showing the triangle here. So please consider this triangle as the enlarged version of A, B and N. for this angle theta. Sine of theta is equal to opposite side divided by hypotenuse. So theta's opposite side is Bn, and then the hypotenuse is AB. Okay. Then what do you mean by Bn? Here we can take Bn as BP minus AP. Okay. Then the AP can be approximately equal to NP, where BP minus NP, PP gets cancelled and Bn becomes the path difference. So hence by this we can write it as sine theta is equal to n lambda divided by A. Okay. Then taking the A on the left hand side, we can write it as A sin theta and is equal to n lambda, which is an equation for the path difference in the diffraction at the single slit. So by this we have to get the proper equation for the central maxima as well as central minima. So by taking this equation, the path difference can be noted as the point P. So it's the point P. P is bright fringe. If and only if. So P is a bright fringe if and only if there is a formula. You can write it as A sin theta is equal to 2n plus 1 into lambda divided by 2, which is an equation for central, secondary, maxima for a bright fringe. Then we have to write it for the path difference for the dark fringe. We can take it as 1. For the second one, P is a dark fringe. P is a dark fringe if and only if you write the equation for A sin theta is equal to n lambda. Then where n should be equal to, in the case of bright fringes, the n should be equal to 1, 2, 3 and 4, where if we put the 1, 2 and 3 in the place of 2n plus 1, we will get 3 lambda by 2, comma 5 lambda by 2, comma 7 lambda by 2, which are the multiples of odd numbers. So if we consider the equation A sin theta is equal to n lambda for dark fringes, it will come as lambda, 2 lambda, 3 lambda, etc. So these two are the conditions for the diffraction at the bright fringes as well as dark fringes. So if you want to visualize the patterns of bright and dark fringes, we can consider it as this kind of structure. Here, this is called central maxima, which is a bright fringe, and this is a secondary maxima, again a bright fringe. If we are considering the lowest troughs are of secondary minima, and this is third minima. In the same way, if you consider this side as a plus, it's a plus side and this is a minus side. Okay. Then for this we can consider it as lambda, minus 2 lambda, minus 3 lambda. Here we can consider it as lambda, 2 lambda in a plus order. If we are taking the secondary maxima, this will be considered as 3 lambda by 2 and 5 lambda by 2 and 7 lambda by 2. As I have already told you in the equation that 3 lambda by 2, 5 lambda by 2, 7 lambda by 2, I have written the equation like 3 lambda by 2, 5 lambda by 2 and 7 lambda by 2, and here it is minus lambda by 2, 2 lambda by 2 and 5 lambda by 2. So these are the conditions for the diffraction maxima and the minima in our equations. This kind of diffraction of the light at the single slit are usually used for the spectrographical instruments such as specs and other transmission instruments. Let me solve some problems. A Fraunhofer diffraction at a single slit is performed using 700 nanometer light. If the first dark fringe appears to be at an angle of 30 degree, find the slit width. Let me note down the given data. The wavelength of light for the Fraunhofer diffraction is 700 nanometer and the angle of diffraction is 30 degree, and we have to consider the and find out the slit width here. So what we have to do? And we have to apply the formula. The formula is A sin theta is equal to n lambda, which is used for first dark fringe. The formula is used for first dark fringe. Put the value of A, put the value of theta, which is equal to 30 degree, and n means 1 because it is the first order, and lambda is 700 into 10 to the power minus 9 as it is a nanometer. So take the variable to the left hand side, then 700 into 10 to the power minus 9 divided by the angle sine 30. Okay. Then by using the calculation we will get it as 14 into 10 to the power minus 7 meter. So this is the slit width of a Fraunhofer diffraction slit. Let me solve another one problem. Calculate the angular position of first minimum in Fraunhofer diffraction at the slit width of 10 raised to minus 6 meter if it is illuminated by a light of wavelength 4000 angstrom. So let me note down the given data. The slit width is 10 raised to minus 6 meter. It is also called 1 micrometer. 1 micrometer, and the wavelength of light is 4000 angstrom. Lambda is equal to 4000 angstrom. Okay. Then we have to again put the formula as A sin theta is equal to n lambda, where a is equal to, in the previous problem we are not given with the a, but now we have the data of a, so we have to put the value 10 raised to minus 6 sin theta is equal to n is 1 into 4000 angstrom, 4000 into 10 raised to minus 10, because it's an angstrom which will be in the 10 raised to minus 10 value. Take variable to the left hand side. Sin theta is equal to 4000 into 10 to the power minus 10 divided by 10 raised to minus 6. So by simplifying this, we will get the value of the theta as 23.57 degree. That means the rays which are bent at the diffraction are of angle theta of 23.57 degree angle. Thank you for this opportunity to teach the students.